today's session, we're going to begin a new section of the syllabus. So this particular section focuses on algorithmic thinking, especially algorithm design and problem solving. We're then going to move on to data types and structures, which is Unit 10, and hopefully on to programming, which is Unit 11, followed on to software development and the program development lifecycle, which is Unit 12. Just in case you're wondering, we finished 1 and 2, and this series of lessons will finish 9, 10, 11, and 12. And then that's more than half of your syllabus covered already because there are 12 units at AS level. After that, we'll move on to things like hardware, processor fundamentals, system software, and all the rest. So let's begin by looking at abstraction today and also a technique called decomposition and how we use that to break big problems down into little chunks. Now, you would be familiar with these terms at IGCSE and previous to that. However, we're going to delve into a bit more deeper to look at how program developers or software developers take problems which are often quite huge and remove all the unnecessary information that's out there and try to break the problem down into simple terms which allow us to create code for it. So let's start by looking at what a computer is and what it actually does. At the very base level, a computer performs calculations. To compute basically means to calculate. Nowadays, computers can often perform billions or even quadrillions of calculations per second, which are so much more compared to the ENIAC and the Colossus, the first few machines that were out there. A computer also remembers the results of these calculations, and often data in the range of hundreds of gigabytes or even terabytes is stored through the use of hardware like solid state devices or hard drives or magnetic tape and so forth. So two main things, performing calculations and remembering the results of these calculations, allows a computer create massive worlds to work out the solutions to complex problems. To do that, it needs to obviously have hardware, but to solve those problems, we need to actually understand what variables, what the scope of that problem is, so we can go about creating the software necessary to solve it. And this leads us to problem solving using computers. Programming skills, things that you're learning right now, cannot be passively absorbed. What does that mean? Well, that means that if you're listening to how somebody programs a piece of code or you're watching a video, you're never going to learn how to code. You've got to experiment. You've got to take existing code and you've got to start playing with it. Without practicing problem solving and without practicing coding, you're not going to be able to understand how to develop new pieces of code. So look at existing code that's out there, download it, copy it, run it, enhance it, tinker with it. That's the best way of learning programming. You need to be aware of the basics, things like data structures, iteration or loops, selection, choosing one branch over the other, procedures and functions. And without that, obviously, it's very difficult to break bigger problems down into smaller chunks because computers in the end only know what you tell them. They don't currently have the ability to learn from their own mistakes and develop new code. Yes, we're working on it, and you'll be covering some aspects of it when we look at artificial intelligence in year 13. However, at this moment in time, we create the data sets, we create the rules that allow a program to operate, and that also applies to artificially intelligent programs. And yes, they might be able to learn from their own data sets, but very rarely do they create original pieces of code at the same level of quality as we humans can. And one of the reasons why that's because tasks have to be rigorously designed. Practice is essential. The stuff that we hate to do at times, pseudocode and flowchart, these are techniques which are very crucial to learn. And tracing programs is an effective way to find mistakes in your own designs before you even start the process of coding. The computers are very good at that. However, they're not quite there yet where they can understand the nuances of talking to a human being and the kind of problems that are out there, we might be able to talk to people and work out, well, okay, this is what the person requires. Often, when the person isn't telling us what they require, computers aren't at that stage. They will just use the data that they're given, and based on the data, they can execute something. So, for a new programmer, finding out how to use pseudocode and flowcharts and trace tables is a must. So, before we continue on, let's do a bit of a prior knowledge check. Can you write procedures and functions? Can you write simple algorithm? Do you know what it's meant by structured English? What is a flowchart? What is pseudocode? Now, if you can do all of that, fantastic. There's a short little test there on screen. Would you be able to draw a flowchart for a program that works out the average for a set of input integers? Would you be able to write the pseudocode for it? Would you be then able to code it in Python? Now, if you can't do that, you're absolutely at the right stage to continue on with this particular section. However, if there's something that's missing from the list and you're not aware of that, you might want to find that out before we continue. So dig up your old notes and make sure that you're familiar with all of these. And when you're ready, let's continue on. For a new unit, these are some of the terms which will come up again and again, so you need to be aware of their definitions. What we mean by abstraction is that it's a process of extracting information that is essential while ignoring that which is not relevant to the solution. So the best way to think of that is a map. Often you can have maps where we remove features like how the house looks like down the street, or what the park looks like, and we just focus on things like street names. Decomposition is the process of breaking down complex problems into smaller parts. And you've been doing that for quite a while throughout your studies. You know, how do you do revision? How do you devise the entire IGCSE syllabus? You probably broke it down into different units, and then you created flashcards or all sorts of other techniques to do that. That's an example of it. Like, how do you make a cup of tea? You break it down into different chunks, and that's the process is decomposition. And finally, there is pattern recognition, the identification of parts of a problem that are similar and can use the same solution. So think about when you use functions or create subroutines. Okay, this part of the code does exactly the same thing. Instead of writing it 10 times, let's just extract it and keep it separate and call it when we need to. And that's basically what pattern recognition is. So let's start by looking at abstraction. Abstraction is basically extracting essential information and discarding the rest. And it involves developing simplified models of real world scenarios and situations. And everyday examples we already talked about include maps, but then there are others like calendars and timetables. And the benefits of all of this is that often by removing all of this unnecessary information, development time is reduced because we're not coding, for example, in a map, how a house would look like. We're just coding what the map should be used for, which could be simple navigation. And this results in smaller program sizes, and that entails better customer satisfaction because you are doing exactly what the customer or the client wants. So abstraction has a lot of benefits as well, but in essence, it simply means just taking the essential information required to solve the problem and discarding the rest. So 3 simple steps for abstraction. First, identify the purpose. What do you need to do? Second, identify the sources of information or data available to you. And then third, identify what is essential out of all of that and what is extraneous. That extraneous information is not required. And think about the 2 maps that you see on screen. The left one is a tube map. The right one is obviously a navigation map. And you can see that there are features in the right map which are non-essential for a tube map. A tube map just needs to know the lines that connect the various stations. It does not need to know whether there's a river nearby or whether there's a mountain or there's a grassland or whatever else. All it needs to do is know the stations and the lines that connect it. Of course, both are maps and both are abstraction based maps of the real world because the real world looks quite different. However, they are fit for different purposes. The next thing we're looking at is decomposition. And this technique involves the process of breaking down a problem into smaller components or tasks. And these tasks are further divided if needed until each part is easy to understand and implement. Now, In computer science, we've been doing this for years. I think you've done this in the past. You're given a problem, and if I was thinking about the problem that we talked about earlier, where you had to design a flowchart and pseudocode about input a number of integers, work out the total, divide it by the number of integers to work out the average, and then output the results. Things like that. You're given a problem and you have to code it, and you do that by breaking it down into different chunks. Okay, how many integers are need to be input? If you're given that, brilliant. If you're not given that, you keep a counter and you count how many integers are put in. And then you keep a running total. How do I add them up? That's another problem. How do I work out the average? That's another problem. How do I output the results that I calculated? That's another problem. So each aspect is broken down and subdivided until you can generate a line of code or one step in your flowchart or one line of pseudocode. And that's basically what decomposition is. Keep on breaking things down until you get to that single step of code or pseudocode that can work towards solving a problem. Now, often you might end up with a seemingly simple problem, but when you go down the route of decomposition, that simple problem can turn out to be quite complex. And often people don't realize that. Sometimes they look at a task and say, oh, that's okay, that's very simple to code. But when they get into breaking the problem down, they find that, okay, there's a lot of things that they weren't aware of that they need to do. And decomposition can end up saving you a lot of time and allocating the right resources that might be needed to solve a problem. Now on screen, you can see an example of how we can use decomposition. In this case, we've got an inverted tree approach. You've got the program, which can be divided into two different modules, which can be further subdivided into different modules, and you can keep breaking it down. And then eventually, once all the modules can be coded uniquely to solve whatever they need to do, you can then allocate this to different programmers who can start actual coding. So decomposition normally uses this type of a tree structure or a hierarchical structure to break things down into little chunks. In the exam, if you're given a problem to break down, you would need to use this kind of approach, or you might be given this kind of structure to help you identify what you need to do. The next stage or the next technique we're going to be looking at is pattern recognition. Now, pattern recognition is very important in computer science because it helps us identify those parts that are similar and could use the same solution. And this leads to development of reusable code. Think about subroutines, functions, and procedures, and we use that all the time. There are library routines which are built in to programming languages to save you that time. Because you know that random, for example, is a bit of code that needs to be used by lots of people. You code it and you make it available through the programming language. And that saves you from coding your own random function. Time is another example as well in Python. Now, each final part can be written as a module of code, and then reusing these modules of code can help you save that time. A good designer will always be on the lookout of which modules in the decomposition stage can be coded together, where reusable code can be utilized within the program itself. So by the end of this lesson, you should now be familiar with the terms abstraction, what the purpose of decomposition is, and how can pattern recognition help in developing software. These three terms you need to know inside out because they will be utilized in the exam and throughout the various sections that we are now going to be studying. So make sure these key terms are written down somewhere in your exercise book, and I'll see you in the next lesson.